In our physics lab on Tuesday, we were asked to make a motor using a battery, piece of wire, a magnet, and a screw. And as a bonus, we had to figure out a way to calculate or count the rotations that the motor would make every second, or in other words, in hertz.
I'm gonna have to science the shit out of this.
So the first problem was trying to figure out how to make a motor out of the things that we've been given. So we asked ourselves, what exactly is a motor? And what are the components that we need to make a motor? Based on stuff that we've seen in everyday life, we know that motors have something that spins, you can call it a rotor, and something that powers it up, and in some way it has a force that spins the rotor in one direction or the other direction. We picked the screw as the rotor. Problem was how to allow it to spin freely. We tried placing horizontally like this, with the magnet not shown in the picture stuck underneath. But that obviously didn't work, because there was just too much friction. Then, thanks to some helpful hints, we used the permanent magnet to magnetize the screw, and then stick the tip of the screw onto the end of the battery. The very small amount of contact between the screw and the battery meant there's very little friction and it spin really easily. So we set up our motor like this. Through some trial and error, and lots of helpful hints again, we found that touching the wire to the side of the permanent magnet would make it spin. So we figured there must be a force that's causing the screw to spin. When we connect the battery's ends with the wire, the electrons inside the battery move from one end to the other, the negative end to the positive end. Electrons are these charged particles, and they can interact with a magnetic field. And the magnetic field can actually apply a force and push on the electron particles as well. What's happening in our experiment is the electrons flow into the magnet like this. The little magnet that we use has a permanent magnetic field which pushes on the electrons and creates the force that makes the magnet and the screw spin. To figure out the direction of how things move and which way the screw will spin, we use the right-hand rule mnemonic. And it goes like this. If the electrons flow in this direction, then the current is set to flow in the opposite direction. If the current is in this direction, and the magnetic field is in this direction, then the force is in this direction. This force is called the Lorenz Force. It's created when a current moves perpendicular to a magnetic field. Through a bit more of trial and error, we found that the motor actually didn't work if the wire was touching the bottom of the magnet. Now that we know this, it all makes sense, because when the current is flowing in this direction, but the magnetic field is also in the same parallel direction, the electrons are just being pushed in the wrong direction. There is no spin because they're being pushed in the wrong direction. We also found that we can reverse the direction of the spin of the screw if we flip the magnet upside down. Again, using the right-hand rule, this makes a lot of sense. Now, the current will flow like this, and the magnetic field is like this. So the force and the spin will be like this. We need to calculate the number of rotations per second that the screw would take. The problem was that the screw spun really quickly, too quickly for us to see with the naked eye. Plus there wasn't any special markers that show us how many times it was spinning. So we used a black marker, side of the magnet to make the rotation more visible, and a slow motion camera to capture the rotation to make it possible for us to count. We captured about 6 seconds of footage, but only needed to count the number of rotations for 1 second. Over 2 different recordings we found the numbers to be 18 and 20 rotations per second, so we calculated an average of 19 Hertz. Finally, I'd like to mention there is some uncertainty in our calculations for the frequency, reason being we didn't apply the current for a long period of time. If we did, the rotations would be too fast for us to count even with our slow motion camera, so we relied only on the initial momentum of the spin. This meant that we didn't actually reach the top possible speed for the magnet and the screw to spin, so our frequency may not actually be an accurate value. And second, we'd been messing around with the equipment for a while, possibly shorting out the battery prematurely, possibly even enough to degrade it to the point it didn't work to its full capacity.